The following is a recording I made about 7 years ago at the Coast Guard Academy, and I had it uploaded on another account. So I want to move it over here. So this is just an introduction, and I might trim off the beginning of that one and merge the two together. So here we go. This is me 7 years ago. Welcome to another video for fluid mechanics. Today we're going to do pipe system and pump curve matching. So here is the problem I've created. It features a pump that's going to move water from one tank to another tank, starting at 60 psi and going to 120 psi. It goes through a globe valve, then through a branch T right here, then through a check valve, through the pump itself, through a couple of elbows, through a globe valve, and there's a distance of 30 feet between the surfaces. We're going to use the this version of the Bernoulli equation. Notice that it has the head we use a subscript S, I believe for shaft, but that's the pump head that's created, and here are the losses. Losses broken down into major losses and minor losses. By major we mean pipe losses, so this is the sum of all the length of pipe, and the minor losses are through valves and fittings and so forth. So it's the sum of all those K factors. And we're going to find the flow versus pressure curve, actually head versus flow curve, and we're going to match that to a pump curve. So here we go. And we're going to make an Excel spreadsheet to do it. So we can discard that and continue recording. Now here's an Excel spreadsheet that's very similar to the one that's loaded up on D2L for you to use. The only difference is that I've moved the pump curve over to the side, and I put the diagram on here so that we could look at it. I've also put some equations here for reference so that we can see where the ones that we come from. So some of the things that I've done for you to start off is I put here's all the inputs right here are going to be in yellow, and over here to the side I've also put together a small little table with all these little K factors so you didn't have to enter them in, and multiplied by the quantity and then sum them all up, right? So let's start off. I'm going to go ahead and enter in a lot of the numbers that we know from the problem, and then we'll put in the equations to be able to generate the stuff that is the point behind this. So we start with 60 psi at 0.1 right here, and then the velocity we could at the beginning right here at what we're going to consider 0.1 is going to be 0. The Z1, we'll go ahead and call that 30 feet, and we'll call Z2 is 0 feet, so that'll be the reference right here. And then P2, that's the 120 psi that I have in my system, so 120 psi. And the velocity is going to be 0 because we're going to go to a point that's right on the surface. The total length of all the pipe, you can add this up. I went 40 plus 40 plus 10 plus 10 plus 20. All together, if you add those together, you get 120 feet. The diameter is going to be 2 inches. I've placed this as feet though, so I'm just going to go ahead and say 2 divided by 12. And the roughness I can look up in a table. We're going to use galvanized or commercial steel pipe. This is 0.0003015 is the value there. The density, this is going to be water, so it's 1.94 slugs per cubic feet. And the viscosity, we'll treat it at the standard temperature, so it's 2.34 e to the -5 pounds second per foot squared. Now we'll start entering in equations such as the area here, pi divided by 4 times that diameter squared. Okay, so that gives us, let's see, I want to make sure we get a couple more significant digits. I should make this thing, okay. So that's what we get for the area, and we'll take the roughness and divide it by the diameter, so we get that relative roughness, and we want the length divided by diameter. Right here, so we get those terms, and then I'm just going to copy for this K, I'm going to copy this total that we get from over here. So let's start counting up our fittings. We have an entrance, I'm using K as 0.8. There's a couple other different values you could use, but I'm going to stick with 0.8. And so there's one entrance loss. We're going to have threaded fittings, we'll choose them to be threaded. We have 2 threaded 90-degree elbows. Right, and we have no flanged fitting, so we have a threaded branch right here because it's coming down through the T and going out the side. So we have one of those. If it was in line, that would be like as if it was going through the straight part, right? So, but we don't have it. We have 2 globe valves. I'll mention that the symbols I'm using are kind of it's kind of sketchy. There's kind of some disagreement as to what the correct symbols you should use, but I just pick some. Swing check valve, I'm going to have 1. There's no strainers. There's no other stuff that had some kind of miscellaneous, but there is an exit, so I'll have 1 exit. So I get 28.8 is going to be my total K. Now I'm ready to go down and start filling in this table that's going to make up the graph. I'm going to do a little thing here that to make our lives easier. I'm going to go ahead. I know ahead of time that it's 320 is the total range that I want for my gallons per minute. You'll see how that works in a minute. Hopefully I'll show you some. So we have, we can start off with this first line. I'm just going to put zeros in here because that makes sense. It's not critical that you put in the equation for the first line. Right here, I'm going to go ahead and I'm going to take 0.0, let's see, 5. So it's like going to be 5% of this flow range, right? So I have that flow range, but what I'm going to do with that is I'm going to set that as with the F4 button with double dollar signs. Okay, I'm going to copy this and bring it back down, but I'm going to go ahead and modify that one, and I'm going to add the row before, right, without the dollar sign. So what I should get is an incremental increase. I could drag this all the way down to 300, so you can see 320. So you can see what I've done right here is I've counted by 5% and made my full range. That'll be the range of flows that I have. Divide that by 7.48. That's the number of gallons per cubic foot, and divide it by 60, and that ends up giving me the cubic feet per second, and I could drag that corner down and populate all of those. All right, now for the velocity, that's just going to be the Q, the flow rate, divided by this area that we have, and so we should get a velocity in feet per second, which we can drag the corner down. Okay, see, here's a classic mistake that's easy to make, is that I forgot to hit the F4 button and make that so it's got the double dollar signs on it. Now drag it back down. It's very easy to make that mistake and overlook it. Now, for the Reynolds number, we can grab the velocity. All right, so the Reynolds number, as I recall, is going to be density. So this is density, and remember to use that F4 button that time, and then multiply it by this the velocity that we found right there, right? And that's not an F4, and then multiply it by the diameter here, that is an F4, and then divide it by the viscosity, once again F4. Right? So we get a Reynolds number right here, and we can drag this down. Okay. And now here comes a difficult one. We need the friction factor. which would normally have to look up in the Moody diagram. But we can go ahead and use this Colebrook equation right here. This is the one that how we've seen it before in the notes. The Colebrook equation, which for some reason is upside down, has the square root of the friction factor that we want. Now I've rewritten it right here, just so that you can see what the basis of it is. I'm also going to do a little bit of a cover here because it could potentially be a laminar flow. So we'll go ahead and do an if statement. So I'll go equals if, and then say if this right here is greater than 2100, right, then I'm going to use this big equation, which is going to be 1 divided by the quantity of negative 1.8 times the log 10, okay, that's the regular log, of the quantity of the roughness, relative roughness, right, that we have up here, okay, but we need to make that F4 because that's going to remain the same, divided by 3.7, okay, that raised to the 1.11, right, plus 6.9 divided by the Reynolds number, which is right here, but I have to go below it and then go back up one to be able to get that. And now that Reynolds number is going to change all the time, and so now we need to put a parentheses right here, okay, close the parentheses, and now we need to close another parentheses, all right, and then I think one more parentheses we have to close, raise it to the second power, and I believe we're done with this equation right here. We just need to finish up our if statement. We take 64 and divide it by, once again, that's got to be a Reynolds number, but I have to click on a cell below and then go with the upwards key to be able to get it because my equation's in the way. Now I think I've got everything. We'll double check with numbers I've used before. All right, and I get a 0.0268. Okay, so I entered in that equation correctly. I just want to drag it real quick just to see if I did all my dollar signs correct. Yes, okay, so I can drag it the rest of the way. And now that's the friction factor. Now we want to go for the head losses. We said that the head losses are major and minor. You notice the form of them, we could combine them, so I'm going to go ahead and do that. So I'm going to take, for here, I'll say equals the friction, okay, I'll do the quantity, the friction factor times L over D with the double dollar sign, and then I'm going to add that. Okay, so that that's what I've just done this portion. Now I'm going to add it to the sum, all these right here, the total KLs, and I'll make an F4 right there, right? So that whole quantity times the velocity squared divided by 2 divided by 32.2, and I should get my head there. So 2.0, okay, that looks right. One trick that you could do once you have a table started, and so you have some stuff filled out to a column to the left, you could just double click on that bottom little corner right there, and it'll populate the rest of the table. But the day I found out that, boy, was I a happy person. That was really exciting. I know, I live an exciting life. All right, so now we've got the minor losses in there. Now we want to try to get the H. Well, I called it HP here. Just for consistency, I'll call it HS. I think I changed the student version of the Excel spreadsheet so that it reflects that, but I needed to change it on mine. Okay, so I've rewritten this Bernoulli equation that we discussed. I've rewritten it so it was equal to the pump right here. And because I have the losses right over there, it makes it a little simpler here. So I'll say this is going to be equal to the quantity of P2 to make it an F4, and then minus the P1 F4, and then that whole thing is going to be times 144, so that makes sense. And it's going to be divided by the density with an F4, and also divided by 32.2, because we actually divide it by the specific weight, but we use the density and gravity, so we get this. It's the same number. All right, and then now we can go to the velocity 2 minus velocity 1. That's referring to the velocity at the very beginning and the velocity at the end, but recognizing that the velocity would change with the flow. I'm going to leave that out. So I'm going to take the Z2 minus Z1, but I need to make sure I have the double dollar signs on here. So Z2 minus Z1 here with the F4 on there, okay, and then I'm going to add in the losses, which of course got hidden underneath there, so I'm going to hit the cell below it, hit the up arrow so I can get to grab a hold of that. So that should give me 108.3. Okay, that's what I had before. Now I'm going to drag this down, and I'm going to double check my numbers, and that looks like what I got previously, so it appears to be good. Now finally, what I want to do is I want to find power, because that's often what I want to know. Now the power is going to be equal to the HS, the pump head, times the flow. Let's see, where'd you go here? Times the flow in cubic feet per second, right? Times the density, but with an F4, and then times 32.2. Right, so of course there's nothing happening. There's no flow right here, so that doesn't. So it's 0 right here. So I double check what I've done before. Okay, so I got these values. So I've set that up right. So that's an equation that we've used where we found head times flow times specific weight was equal to foot-pounds per second. And then we can divide foot-pounds by second by 550 to get horsepower. And now we have a range of horsepower. So I can get rid of this diagram, and I could show you the remainder of this process. Insert a curve. I'll do one without points, so this is going to be a smooth curve. So I insert this smooth curve, and I say select data, and I can add select data. I'm not going to create a name for the thing yet. So I'm going to take the X data, and the X data is going to be gallons per minute. We're going to take, and we'll go through this range, and then we go for the Y data. Is this going to be HS? Okay, we did the power, but that might be something we might need later. And we come up with this curve. I'm going to do a few things that I'm sort of a stickler about. I'm going to get rid of these horizontal lines, get rid of the legend, and I'm also going to, you'll see why in a second, right click this. Right, see, I'll right click and I will make no fill on the background, and I'll go and right click onto the field in the center on the plot area and no fill inside there too. And you'll see why I do that in a second. I'm going to fix these numbers because they always bother me, and get rid of the decimal place. Doesn't make any sense. And I'm going to change these again in a second. But here's something that I find quite useful, and the reason why I got rid of the fill is I can take this pump curve right here and superimpose it underneath. Well, I guess it's underimposing, huh? I could put it underneath this curve that I'm generating. So I'm going to stretch out the curve I've generated, and you can see that it's on top. So it's a little bit confusing, but if you grab a hold of it, and you grab a hold of the corners inside the curve you're making, and you drag up this corner and drag it to right about right here. Okay, I'll do it over in this corner so you can see what I'm doing. I'm getting to the 0 point right here, And then I'll also grab this, and so I'm going to try to match it right up. I'm matching the square of it up. And now I'm going to change my range, right-clicking on the Y axis here, and I'm going to make it from 0 to, it looks like it's 600, okay? 600. So what I've done is, you'll notice it matches that 0, 100, 200, 300. They match up with the graph. I'm also going to do the same thing for down here. Right now, it appears that this is in 40 gallons per minute increments, and it goes up to 340 if I'm not mistaken. So 340, right? Looks like it maybe. Let me double check on that. And it goes by increments of 40. So let's see what happens here. All right, no, so it didn't. So it must be, okay, that must be 360 it must go to. That would make sense, wouldn't it? All right. So 360, yes, okay, I can see the 320, they all line up. Now what I can do with those right here is I can actually, now that they've lined up, I could put display tick mark, and you can go none. No, that's not the tick mark, excuse me, that should be outside. But axis labels, you can go to none. All right, yep. And you could do the same here for this one, axis labels none. Now they're not in the way. And what we've done is we've superimposed this curve right on top with the same scale as our pump curve. And the way we match these is to look at our system curve. That's where we've plotted on our graph, and see what the intersection is with various pump impeller sizes. This is a generic pump curve right here, and you could see that if you so chose, if what you wanted out of this pump system was to get 220 gallons per minute, you would see that you would get pretty close, at least, with having an 8-inch diameter impeller on this particular pump. But if you wanted less capacity, and you would put in and maybe get the 7-inch diameter. And what they usually do is they take the impeller and they machine it down from its largest size. You could also pull off of this graph what the pump efficiency would be, and you could also pick off it what the power would be for this pump. You'd also take a look, and you could see the operating point, which is what the intersection is of your system curve and your pump curve. And you come down here, and you could find what the net positive suction head required is for the pump at that speed, at that flow rate. And you could go over to the right, and you could find what that value is off of this other little curve that's on there. So that's the process of generating this spreadsheet. One last thing, because I think it would be important to see. I often see people print things out, and it looks pretty ugly. They could, maybe it jumps over to other pages. So I'm just going to highlight the stuff maybe I want to get printed on there, and hit page layout. Go to print area and set the print area. All right. Now I could go over to print. I'll go to that right here, and I could. Okay, so this isn't doing it for us, so we need to hit print preview. This is the old Excel here, and in print preview we see that it's falling off the edge, I believe. No, it is. No, it's fine. It's, it has actually gone in there. But if it didn't, what we would do is we go to page setup, and we would fit to one page. And perhaps if it wasn't already in portrait, we would go there instead of landscape, and then we would maybe balance the thing out horizontally so it's even on each page. All right. So that's the last thing, I think. We could have also, if we wanted to make it look, have it done at once. Let's see. We could have gone and grabbed this whole thing, perhaps, if we wanted to. And before we did that, I think I would want to get rid of this border, no line. So we get rid of the border right here. And I could grab a hold of this whole thing and make this the print area. Right here, set print area. and then I could go to print preview, right? And that doesn't look all that great, so I could change to landscape here. And that might be too small, so I might also want to go and print right here, and you can go to the margins, and we could make the margins much smaller on the left. We don't want to go too small because the printer might not be able to do it. But now we can make it, we could crowd out the margins, and we could see what the thing looks like. So that's it for this tutorial, and hopefully you'll be able to mimic what I've done and then modify this to solve other problems. Thank you very much.